Thank you very much, and thank you for the introduction, and thank you for giving me the opportunity to come back here. This is a place I have been before, up the mountains and all the way along the coast. I love it, it's beautiful, so I'm very, very delighted to be here in person tonight. I'm working in the Peatlands, in the flow country of Caithness and Sutherland. I do work right across from Sandwood Bay to the Caithness coast. And I do anything that's got to do with peatland. If it's got peatland, if it's got peat, I'm in. So today what I wanted to do really is just go over a few of the bits of research that we've been doing over the last few years. There's been quite a lot of work involving lots and lots of people. So I've also got a little bit at the end where I'm just introducing some of the people that have also provided the data, my students and the people that have been involved in this research. So hopefully we'll go on a journey of what we've learned about the peatlands by all the work that we've been doing in the flow country. But just so we know what I'm talking about, this is really broadly the area that we talk about when we talk about the flow country. On the map you can see the blue is the areas of peat, and the yellow line is simply the outline of the area within the flow country that has now been inscribed as the World Heritage Site. So for me, it's just important to make the distinction that the research that we do is not, and the work that we do is not limited to what's in the yellow line. It's really right across, even if it's not part of the boundary of the flow country, we still work on it and we still work with the people all around those areas. So we're here. Just in the map, and there is still quite a lot of peat outside of the kind of Caithness and Sutherland, and the main reason it's not called the flow country in this bit, it becomes much less continuous. It's much more discontinuous, little pockets of peat. But much of the research that we've done, the same principles will apply, the same ideas and the same concepts will apply to those smaller pockets of peat. The difference is that the very large continuous expanse of peat allows some of those much bigger landscape processes to be easier to interpret and to see at that sort of scale. But what is peat? So I thought I'd start with this, so just to make sure we bring everybody along on the journey. Peat forms in any places on Earth where there's more carbon going in than carbon going out. That's the bottom line. And how it works is that plants do photosynthesis. By doing photosynthesis, they take in the carbon dioxide out of the atmosphere and build plant biomass, leaves, fruits, stems, everything else. In peatlands, the conditions tend to stop the decomposition process that would return that carbon back out into the atmosphere. And that's because it tends to be wet, lots of water, anaerobic condition, no oxygen, the microbes can't quite decompose, but also the plants that make up the peat have properties that make them more difficult to decompose. And all of these processes lead to carbon going in, very little carbon going out, and that carbon doesn't go out from the atmosphere or in the water, and on balance it accumulates as peat. It builds up over time. And in the northern peatland system, peat builds up very, very slowly. So this is not a fast process. It's not something that happens very quickly. The plants just do their business and the microbes don't quite do their business, and this imbalance just maintains over time. And in the north of Scotland, it accumulates at a rate that would translate to approximately 0.6 millimeters per year, so a bit less than a millimeter per year. So I'm 1.48 meters. If I was a bog, I would be a bit less than 1,400 years old. And this is important to understand. So it's not something that happens quickly. So when we talk about the role of peatland in terms of the global climate change, we can't compare the rate at which they store the carbon to that of a forest. But what's important about peatland is that once they've stored the carbon in the peat, it just stays there. As long as the condition that maintain this imbalance can be present, so as long as it's anaerobic, there's no oxygen, it's cold, it's wet, it's a bit miserable, this is perfect for peat. And that means that the carbon that goes in the peat can stay for thousands and thousands and thousands of years. It becomes locked away. And if we think about the forest, the carbon, the same processes happen. There's photosynthesis, buildup of organic matter. all of that is, or much of that is above ground in the form of trees and the plants underneath the canopy and everything. But there's a lot of gaps and air in between that. And when the tree dies, the carbon returns back into the atmosphere. And that happens over time scales of maybe hundreds of years. In the peatland, the carbon is invisible because it's below ground, but it builds up very densely and it stays there for much longer periods of time. So the role of peatlands in terms of climate regulation comes from the fact that they lock away the carbon slowly but steadily over very, very long periods of time. And once it's locked away, it just stays locked away. And all of that happens because of these really intricate feedback loop between the ecology, the plants that make up the peatland, and the high water table that is maintained. So plants like sphagnum, here Sphagnum pulchrum, they have a really good ability to store and maintain water. And they're a keystone species, an engineer species that create the condition in which they thrive. And in turn, these conditions enables them to continue to grow and excludes other species that can't quite cope with that amount of water. And so the species that come and live in peatland and in bogs tend to be very uniquely adapted to these conditions. We find things like carnivorous plants, there's not much nutrients kicking about, so they can get their nutrients from eating insects. We find shrubs and sedges that are adapted to finding the other bits of nutrients that are available without really competing with one another. And all of these species are uniquely adapted to these conditions. So it means that if you have a peatland in a landscape, it brings in a whole suite of species that would otherwise not be there, the very, very specialist species. And a lot of my research in the last kind of 5 to 10 years really has been, we've known for a long time about the ecology bit. We've understood really well for a long time about the hydrology, everything that relates to where the water table sits, how it's wet and where the water flows. And we've known for a very long time that peat is squishy. When you walk on peat, it moves. You've probably all walked on a bog and you've felt it wobble when you get to the edge of a peatland or a peatland pool and you jump and you can see the ripples in the water. Peat is not like the other types of soils that you have. It's not hard, it's squishy. And what my research has been doing with lots of colleagues in the past has been bringing that into the picture a bit more. We know about the ecology, the hydrology, and we think that the mechanics, the properties of the peat, the fact that it's squishy, are really important in resilience. But I don't know if you've ever tried to measure movement on a peat bog. When you stand on it, it moves. It's impossible to measure it on the ground. So we've turned to satellites. And there's a satellite, the Sentinel-1, that goes around the Earth every 6 to 12 days. So if there's 2 of them, they go every 6 days. If there's 1 of them, they go every 12 days. And every time it goes, it sends a radar signal on the Earth. The radar bounces back up. And the radar hits the surface. And if it's wet, it just really hits the surface. It doesn't penetrate into the soil at all. So when it hits the surface and it bounces back, the time it takes to do that gives a distance, or effectively a surface that moves up and down. And as the satellite goes every 6 days, you can build stacks of images where you have the distance that moves up and down. And so what we've thought is maybe we could use that to see, can we from space see the surface of the bog moving up and down? As it fills with water, it should go up. As it decreases in the water, when the plants are using up all the water in the summer, it should go down. And that's what we attempted to do. And then we thought maybe we could use that to understand a bit better how different parts of the peatland are working. And so we did. We built up these time series of surface motion, and what we found was that there were different properties of those signals. So the going up and going down didn't always happen at the same time. Sometimes it went up a bit more and down, so the amplitude of the up and down was different. The timing was different. The long-term trend, was it slowly but surely going up, or was it slowly, rapidly, or slowly going down? And all of these properties we thought related to expressions of the resilience of the peatland. And so we went out to validate that in the field, compare the measurements that we were taking from the satellite to real measurements in the field of what is the vegetation looking like. Is it really bouncy? Can we feel it? Can we measure it? And so we spent two years doing that. And then this happened. That was in Ireland. So we were right in the process of beginning to understand how the surface motion related to the resilience of the peatland. And then in 2020, in short succession, there were 3 massive landslides in Ireland. So this is a peat slide. So the catastrophic failure of the peat that went. And then we thought, actually, that is the expression of that surface motion gone wrong. It's like the extreme motion that you can get from a peatland. And we thought maybe we could use that same technique. We can look at the surface motion and see, can we see anomalies of surface motion where it would be just moving too much before it fails? And that would be using this mechanical properties of the peat to understand a failure, a breakdown of resilience. And so we did. We used the satellite, and what you see here is this is the same area, so the blackout line on the small square is the same as the blackout line along the actual peat slide. And what we looked is we looked at those series of amplitude and we took out all the extreme points. So we decided we'd go for the maximum extreme points, and these points are the yellow ones on the figure. And what we found out was that not just for this one, but for all the peat slides that we had evidence for, it was always coinciding with points of extreme amplitude. And when we looked back in time, we could see that these points of extreme amplitude were starting to behave like this up to 18 months before the failure happened. And so we thought, with this technique, we could identify the parts of the landscape that are more susceptible to happening, for these landslides to happen. So using the remote sensing and this bog breathing, the up and down, we can look for the anomalies where it's breathing way too much. And then we can see this is an area that's at risk. And this could be a place where we want to do a bit more investigation on the ground, where we can pull resources. So when we presented this evidence to NatureScot, they said, could that be useful for help and for us in terms of managing risk when we do peatland restoration? Because if you do block a peatland and restore a peatland, you bring up lots of water in the system at once. And it may be that in some part of the system, bringing a lot of water will lead to these really big amplitude of motion and could lead to catastrophic failure. And the same with the renewable energy development. They came to us and said, could this be useful if we build a road and it blocks the drainage and it leads to a bit of water accumulating on one side of the road and it starts to move? Could we identify those areas before we build the tracks so that we avoid areas of risk? And that's what we did. And I just chose an example here that's the closest I could find from where we are. And this is an example, so exactly the same. So yellow area means lots of really high amplitude. It could be a risk of landslide. And this is an area where there's been peatland restoration. And what we've identified here is that there's been quite a lot of intervention at the further up the catchment that seems to have concentrated water in this particular area here. And what we've then told, when we've told NatureScot, is we don't think this is an area that's going to collapse tomorrow, but this is an area that's worth going and investigate a little bit more to make sure that any management that happens there is done sensitively so that it doesn't suddenly lead to lots and lots of water going in. And with that, we've done that now across all of these areas of Scotland. So these are all sites where there was plans for peatland restoration to happen. We've fed that information, we've helped them manage the risk, and in some areas they've made the decision not to do an intervention or to do it slightly differently to make sure that those catastrophic failures don't happen. And so that's an example of how we've used this kind of mechanical properties of the peat, the bog breathing, to inform risk management in terms of the really extreme behavior that could happen if there is too much movement and it suddenly moves away. But then the opposite end, That's when it's too wet. But then we've also had periods where it's been too dry. For example, in 2018, we had a really severe drought across much of Europe. And then again in 2021, we had a really, really dry spring. And in the peatland, dry is not good because it introduces oxygen into the peat. And that means microbes can start decomposing, and it means carbon can leave the system. So we wanted to understand what is the role of that squishiness of peat in relation to drought. And what we were doing at the time is we were right in the middle of trying to validate this bog breathing idea with measurements in the field, and then the drought happened. And what we found was quite extraordinary. We were measuring in 2 sites here. So what we were doing, I had Chris and Pete, two of my postdocs, and they were going around with surveying equipment and doing really, really high precision leveling of the peat surface to track whether the surface motion was doing the same thing as the satellite was doing. And we did that for 2 years. That included the drought year, bang in the middle. And we did several surveys over the two sites, and at the same time we were overlapping them with the satellite data. And what we found was that actually not all the parts of the peatland respond in the same way to a drought. And what was really surprising at first was that the pool system, the areas that are the softest, were actually the most dynamic, and they collapsed. And they collapsed irreversibly. So rather than staying up there and the air going through, the pores, the sphagnum pores just start to collapse, and the surface tracks the water table. And counterintuitively, after the drought, that bit of the peatland was the wettest. And on the margins of the peatland, so these are the pools, so that's the bit that it went down by more than 10 centimeters over the course of 2 weeks. So that's a really big drop of the surface. And then on the margins, which are the lines here at the top that you can see, so this is the zero is relative to the surface, this is the drought starting, it goes really well down when it's a pool, and on the margins where the peat tends to be a bit shrubbier and a bit drier, it just doesn't collapse as much. And so in a way it pushes the water to the margins hold it there, and then it goes back in. But when it comes back in, it doesn't come quite right back to the surface. So it's like there's a collapse, and then it goes back up a little bit. And these are at the top the moisture measurement, and as you can see, what we have is the blue line is the pools. It goes down and it comes back up, and it goes back up even higher than it was before. So it starts, the surface collapse, tracks the water table, the peat compresses a little bit, it's wetter. And because it's wetter, what happens next? The sphagnum is really happy, and it grows faster, and it rebuilds that elastic layer that can collapse up and down. And that was one of the first bit of really empirical evidence that we could provide that it was not just the ecology and the hydrology, but also the mechanics had a really, really important role in the resilience of the landscape. And if you can maintain these central areas that can really bounce up and down, and the margin can stop the water from leaving the system, then you're going to have a resilient peatland. And what was really, really good is that the measurements that we took on the ground actually matched the measurements that we took from the satellite. And you can see it here with the blue measurements being the satellite one, and the red one being the ones that we did in the field, and they track each other absolutely perfectly, except when there's really, really rapid movement, then the satellite can't quite cope with really big motion. But otherwise, they track each other really well. So that was, for us, it gave us the confidence that we could reliably use the satellite data, which can cover the whole of Scotland at once, without having to go everywhere and do the field measurements. So it gave us the confidence that it was a reliable technique to use for doing this kind of study. But then the fire happened. So that was 2018, a big drought. We learned a lot about resilience, and then a fire. The largest fire ever recorded in the UK in the Flow Country started near the village of Strathy, and for 20 miles down, it just burned in excess of 6,500 hectares of bog. So we decided to apply for urgency grant money and we got it. And that enabled us to take this fire as an opportunity to learn about resilience when you combine the disturbances. Parts of the fire were on areas that had been forced to bog, that were in the process of being restored. Parts of the fire were on areas that were drained. Parts of the fire were on other areas that had really good bog, so we could compare all of those areas together. And this is what it looked like immediately after the fire. So it was really extensive, but it really covered the whole suite of land uses that we find in the flow country broadly. So that was really interesting. So we used that as an opportunity to learn a bit more about the peatlands. And so this is the fire footprint. So this is at the top of the Strathy, and it went right away down to here, an area in the Forest and Arid Flows National Nature Reserve managed by RSPB. And you can see this is the same kind of footprint. All the blue lines are the historical drains that have been cut. And at the bottom here, they are historical drains that have been blocked by restoration in the late 1990s, early 2000s. So we then set out to compare all of this and work again with our satellite data, the bog breathing, to understand what was going on. And here's a suite of images. So this is every year. So this going up and down, the amplitude, how much it goes up and how much it goes down, this is what's in the map. The darker the color, the stiffer the peak. It means it doesn't go up and down very much. The brighter the colors, the more amplitude you get. And this is what we have. So we have 2016, 2017, they're fairly average years, lots of rain coming in. 2019-18, the drought, the fire in 2019, and then fairly average years after that with a bit of a drought in 2021. And when we look a little bit more closely, what we see, these areas are the areas where there's lots of drainage. They don't move. Throughout the whole series, they just stay blue, they just stay stiff. They don't respond to what's happening. They don't respond to the fact that it's wet. They don't respond to the fact that it's dry, and they don't really respond to the fire either. They lose a bit in the fire, but that's about it. And then when you look at the areas here, these are the areas where there's been drain blocking. These are areas where there's been drain blocking or pool systems, and all of these areas go up and down the most. So what we understand from this is that the different parts of the system, depending on their land uses, will also have a different response to the series of meteorological events that happen, including the fires. And what was really interesting is that there's a drought, there's a fire, and yet this area where it's been re-wetted is really strongly responding to the recharge the following year. So even with a fire, even with a drought, if there's a way to keep the water in the system, it will be really resilient. It'll maintain its capacity to continue to function as a peatland. And we think that this is really interesting because it really helps us understand a bit more how we can manage the landscape at bigger scale, so that we can make sure that there are places that can move up and down, and that we can block the right places and make sure that the water is out in the right places as well. So if we sum up all of this, what we have is, in a near natural peatland or a healthy peatland, we have what we call negative feedback loops. So it's really wet. If there's a drought, it shrinks. It's really high moisture because it's shrunk. If it's high moisture, when the fire comes, it can't really do much because it can't ignite the peat in the first place, and everything is wet anyway. So it recovers really quickly, and it can build up that soft layer again. If you drain a peatland, if you make it much stiffer, if you degrade it and you lose the capacity to go up and down, then you turn the negative feedback loop into a positive feedback loop. The peat is drier, so rather than going down, it cracks if there's a drought. If it cracks, it means that the plants grow bigger and there's more air and more space for a fire to burn more severely. And if you burn more severely, it attracts the plant that likes the fire, like Calluna vulgaris. That would be a fire-loving plant, or Molinia that would become more dominant. and then you end up with a stiffer, drier peat that will just go into the circle. So it's almost like there's a switch from a system that can sustain itself to a system that's just going to run away and get more degraded. And that matters. It matters because, yes, we have the flow country, but we also have a global northern peatland that has been cooling the climate for millennia. And that global peatland system is changing. It's changing because the fire regime is changing, and it's changing because people are degrading peatland. So what we did is that we took our little bit of evidence, and then we spoke to people all around the world, and we built together a global database of all the data that existed on emissions after a fire, peatland states and where the fires were, and then we compared all of that together, and we built a model to understand, are we at risk as the global regime is changing, that our peatland will turn from cooling the climate to warming the climate. And so that's what this figure is representing. The blue color is here. It means the global northern peatland are carbon sink. The red color is here. It means the global northern peatland are carbon source. So it means they go from cooling the climate to warming the climate. And so what we did is we found out where we are. So we're still okay. We're in the blue. So that's currently with approximately 7% of our global northern peatland being degraded, and every year something around 0.4% of our peatland area burning. That's where we are. However, if we double that area without doing anything to our restoration or management of peatland, we could flip into the switch. And that's 2.7 million hectares of peatland burning in 1 year. In any 1 year, that would be not good, but on a long-term average, that would be terrible. And then that was happened in 2023, 18 million hectares of peatland and forest in Canada burned. So there are some years already where we're tipping into that red space where we don't want to be. And because of that, we think that there's a risk that if we project that long into the future, this is where we are now, here, if we consider that there's no burning. This is where we are when we start to introduce the actual data from fire emission. This is where we are if we restored all of our peatlands tomorrow. So we're bringing the sink a little bit more. This is where we are if we use the climate change scenarios that just increase the area burn every year. This is where we are if we increase the area burn and make the fires a bit more severe because the peat is a bit drier because of climate change. And that's in 50 years. And then what we found is that if we have the full force of climate change taking effect in less than a century, all of our peatlands will no longer function as a cooling for the climate. They could tip becoming continuously warming the climate. So that's a bit sad, but we could do something about it. And we think that restoring our peatland is one of the key ways that we can bring resilience, not just to the flow country peatlands, but to the global northern peatland. The more we can restore now, the more likely they will be to be resilient for the future fire regime that is changing. And that's where we can take this positive feedback loop that makes the peatland more and more likely to burn and more likely to be degraded back into a resilient space. And this is one of the things that we've also been doing a lot in the flow country over the last 30 something years. And that's the next part of the talk. So we're going to move from fire to trees. In the flow country, as you probably are aware, there was a lot of afforestation by non-native conifer. And this is the biggest challenge in terms of peatland restoration that we have in the area. And one of the reasons it's a challenge is, as I've just said, degraded peatlands are more likely to be at risk from future climate change. But also these non-native conifer plantation had lots of other negative effects in the peatland, on the species, on the hydrology, on the connectivity, by breaking out the big landscape into units, of fragmented unit with islands of forestry in the middle. And so there's been quite a lot of effort now in terms of trying to restore them, and also quite a lot of effort has been put into understanding exactly what were the effects of the forestry and is restoration working. And the next bit, I'm just going to go over a little bit of the evidence that we've built around what happened when you put trees on the peatland where you shouldn't. How does the restoration happen, and does it work? And can we really bring those benefits that were in the previous slides where the peatlands were becoming stronger sinks? And to do that, of course, you need lots and lots and lots of people and working together. And this is one of the things that I always think is important to mention, is I'm presenting this on behalf of so many people that have been inputting. And one of the things that we found is that the best way of getting all of this evidence together is to work as a group, make a collaboration, all work together, share data, share sites, share expertise, so that it doesn't become the burden of one person, it becomes a really collective endeavor. And that's what we did. And we've brought together all of these different bits. So we've used above breathing, we've looked at water quality, carbon stock, biodiversity, hydrology. So all the elements of my triangle, the mechanics, the hydrology and ecology, we've all tried to bring that all together. And so the big question was, and one of the big questions was, well, we're putting trees, but trees capture carbon, right? They use the photosynthesis, they build wood. And surely that wood, that trees, they grow so big, surely that compensates the carbon that might be lost from the peatland, right? That was the question. People were wondering, do we have any evidence that putting trees on peatland is bad for the carbon? We didn't. And so we decided that there was one way that we could do that. And the way that we could do that is by using volcanic eruptions in Iceland. Because when there's a volcanic eruption in Iceland that's big enough, it sends ashes, clouds of ashes, over the peatlands, and these ashes form thick layers that are thick, very, very small layers, but we can detect them. And when they do that uniformly pretty much across the landscape. And so it gives a very reliable chronological marker that we can use for comparing different sites together. If you go with the basal age, it changes. Some peatlands are a bit younger, older, might have been degraded. But if you use a tephra, you know that you're comparing like with like. So what we did is that we went into the forestry and adjacent sites that were not afforested simply because it was the landowner's choice, so not because they were this different in the landscape. And then we took cores, and from those cores we used a really cool method where we just scanned all the cores with a machine that detects the different oxides, and then when we picked up the oxides we knew we had the tephra, we looked at them on the microscope to identify the eruption, and then we compared how much carbon was above each of them. So how much carbon was in the peat if you don't put trees, and how much carbon is in the peat above the same layer if you put trees. And the difference between the two would tell us how much peat has been lost since across the same period of time since the trees because of the afforestation. And then we also collected all the trees on top. So we harvested the trees, we measured them, weighed them, made sure that we accounted for all the different bits, the roots, the branches, the tips, the trunks. My student Tom, who did that, had lots of wood to process. And we had the weight of the total forestry, so we were able to look at the full picture of the full stocks of carbon above and below ground from areas with and without trees. And what we found was that, in fact, the trees that grow on top of peatland don't grow very well, and even if they look big, they don't build as much carbon as has been lost by the peatland. So in fact, putting trees on peatland is bad for the carbon, is bad for the climate. These trees on these peatlands. And what we found at the site where we did the most intensive studies and accounted for the trees and accounted for the roots and accounted for everything was a net balance of about loss of 20 tons of carbon per hectare. That might not sound like a lot, but if you multiply it by 67,000 hectares of peatland, you get into the 1 million tons of carbon lost because of the afforestation over the course of about 40, 50 years. So that's a lot. That's a lot of carbon that could have stayed in the peatland instead. And the story that putting trees on peat is okay for the climate didn't hold anymore. So we've put that evidence now, and it's now being used to revise the IPCC reporting for peatland and carbon, and harmonizing the problem where we have trees on peat. And so yes, that's bad for the climate. So that was one piece of evidence that we were able to quite convincingly put forward.
Is that 20 tons of carbon per hectare over what time base?
So that was over the first rotation of the forestry, so 50 years. So it's basically a net loss. So if you didn't,
the time base is 50 years.
Yeah. And over the 67,000 hectares of forestry, that would be 1 million something divided over 50 years. So you could get a rate of carbon per year if you like, yes. And so there's been, since the afforestation, there's been changes in the policy and a big drive to remove the forestry and restore back to bog. And we were trying also to identify at the same time, so we know that the forestry wasn't great for the species, it's not great for the carbon, but what happens when you take the forestry? Can you actually return it back to a blanket bog that functions like a peatland? And so we did that across a whole range of different species and different group, including, and that was one of the starting thing that we did, the vegetation. So these are groups of plants, so they're not species, they're the different groups. So we have the trees, the ericaceous shrub, the sedges, some of the grasses, some of the sphagnouses, some of the non-sphagnum mosses, and then some of the vascular plants. And what's really important to look at here is that we have the forest control, where you can see that the biggest line is the black, the trees. It's not very surprising. We're in a forest, there's lots of trees. Then we have a series of sites that have different ages, and then we have the near natural bog control. And what we see in the near natural bog control is lots of bright green. That's the sphagnum, so this is what we would expect. But what we see on those sites that are in the middle is that we don't really have, we've lost the forest species, but we don't really have the bog specialists returning. We have a bit of something in between, including lots of grasses that we wouldn't really expect to see in a bog. So we have species that are coming opportunistically that are kind of more generalist species rather than specialists of either the forestry or the bog. And what we find is that when there's still brash, what it does is that as the brash, the bits of trees that are not collected by the forestry, when they stay on the bog, they just slowly release some nutrients. And those nutrients are just a bit too much for the bog species that like it really poor in nutrients. And there's not enough shade for the forest species. And so what we find is that over time, so if you imagine time after restoration, it's like we have those forest specialist species, they need the forest. So as soon as you take the trees away, they disappear and they go down and they don't come back. But the specialists, the bog specialists, they need all of those other bits. They need the hydrology, they need the mechanics, they need all of these, the triangle to be fully back. And they take a lot of time to come back. And in the middle, you have these generalist species that come in. So you have these different groups of species that exist. So if we were thinking about understanding the success of restoration, if we were just to count the number of species, we would think that we're okay because we have quite a lot of species in the forest to bog site. But when we look at the identity of the species, we realize we're not quite there yet. There's this legacy effect of the forestry that means that the real specialist species that we want to bring, they take a bit longer to come back. And we've done that across lots of taxa. So we've looked at microbes. At the top, you have a testate amoebae. They're like the tigers of the microbial world. They eat the bacteria and fungi and nematodes, and they interact, so they are at the very top of the food chain in the microbial world. So we know they're good indicator species. We lose the really cool species that exist only in the bog when we have a forest, and they don't come back. We've looked at fungi and bacteria and nematodes. We've looked at carabid beetles and moths, and we've looked at birds, and we've looked at everything that we could think of. We've tried to look at. And it's the same story repeated over and over and over again. But of course, when you do research, what tends to happen is that you think about the species, but there's also this other bit, that's the ecology, but there's also the hydrology. And what was really fascinating is that actually exactly the same is happening in terms of the hydrology and the water quality. As soon as you take the trees away, there's some of the elements in the water that disappear, and these elements are the ones that are intercepted by the trees, like some of the cations, the sodium. It gets intercepted by the trees and trickles down on the bog. If you take away the trees, it just goes through. So you lose those. The really specialist water qualities that you would find in the bog, like the acidity, the depth of the water table being just really close to the surface, it takes a long time to come back. And in the middle, we have these flushes of nutrients and dissolved organic carbon and properties that are, again, the legacy of the forestry. So this is mirrored between the ecology and the hydrology in a really, really nice way. So we think that if you can get these bits of the triangle right, it'll come back, but we're not quite there yet. And then in terms of the carbon, if you get these right, it works. But it's a bit more complicated because, in fact, what we found is that you can get back to carbon, to storing the carbon, even if all the rest is not quite in place yet. And this is just because if you can at least have carbon going in and stop the decomposition enough, it doesn't have to be exactly the same species. The process of accumulating carbon can still come back. So we looked at the site that was a site that was about 10 years old, and it was still limiting carbon, so plus is it releasing carbon. When we looked at a slightly older site, it was behaving like a teenage peatland. It started to store even more carbon than the near natural control. And the near natural control, you can see that we have 2 different years and they're broadly the same. So again, the system continues to store carbon, and this one is just beginning to store carbon again. And so that's an indication that you don't necessarily have to have all of the species back before you can return some of the other functions of the peatland. But then we're doing all of this research, working really hard to publish it, and then the practitioner tell us, actually, we've found a new way of restoring the peatland, and we're no longer going to do all of the stuff that you studied. We're going to change it to do something a bit better. Happens all the time. And that's what we just decided. We're just going to continue, but we're going to try to incorporate these new designs into our thinking now and understand if we change the restoration intervention and we make it a bit more intensive, so we remove some of that brash so it doesn't leach all the nutrients in the surface, and we make sure that we create the right conditions in terms of the water table and the pools, and maybe even reintroduce some of the sphagnum species in the pool. Can we shift that curve? Can we take it closer to the beginning and bring those bog specialists back a little bit more? And so far, it seems to be working, but we're still working on building the evidence to publish about it. But our early indications is that, yes, when you do this, when you make it a bit more intensive, you gain approximately 8 to 10 years of restoration outcomes. So the species return a bit more quickly, the carbon sequestration returns a bit more quickly, the water table is a bit more stable, a bit more quickly. And we're doing that, again, across a whole range of different things and incorporating with that all of those different interactions between the ecology, the hydrology, the different trophic relationships, but also trying to understand how they all work together. So this is a lot of work that's going on at the moment that maybe another year I could send one of my students to present to you. And so, going back to this idea that we're doing this super big scale restoration now, we're restoring thousands of hectares of peatland. There's a target for Scotland to restore 250,000 hectares of peatland by 2030. Surely we're not going to be able to send people with boots on the ground and monitor all of these peatlands. And I hear you think already, bog breathing, satellite. Yes, that's what we can do. We can do satellite. We can use the satellite to complement our ecology fieldwork, our boots on the ground, our monitoring, and our data points. And what we can do is define what we think is good. So we know what we're looking for. That's good, the blue line at the top. Lots of amplitude, lots of wiggles. It's slowly stable or going up a little bit. So remember at the beginning, the bog that goes up, it doesn't go up so much that it's going to collapse, but it's able to respond. Stiff, that's what it looks like. It could be good if it's on a margin or on a slope and it's meant to be stiff, but it could also have been drained. That's what we don't want. We don't want the black line. The black line is going down, 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 down. And that means it's losing mass, it's losing water, it's losing carbon. So what we can do is use that broad idea. So we've got 3 categories: high, good, stiff, and degrading. And each pixel that the satellite produces is about 10 by 10 meters. So if you roll that across all of Scotland, all the areas of peatland restored, that's hundreds of thousands of pixels to work with. And what we can do is then classify each of those pixels either by groups of year or year by year. Of course, we do that with computers, and I don't do that manually. But we need a way of doing this. So imagine I give you a fox, and I tell you, you can only classify that fox as a cat, a mouse, or a dog. That's the only 3 categories you're allowed to use. And then I ask you, can you give me the probability that my fox is a cat, that my fox is a mouse, and that my fox is a dog? Well, you might tell me something like, well, my fox is got pointy ears a bit like a cat. It's got absolutely nothing like a mouse, but it looks a lot like a dog. And then change those for series of surface motion. And we do exactly the same. So we take each pixel, we look at the time series of surface motion, and we say, what's the probability that that wiggle is a stiff, a degrading, or a good wiggle? And then we can get a probability that every pixel on every bit of peatland in Scotland is either stiff, degrading, or good. And we can look at how that changes over time. Is a degrading pixel slowly becoming good? Is a good pixel slowly becoming degrading? Is a degrading pixel becoming stiff? And we can understand whether an intervention is working or not working, in the right direction or not in the right direction. And that's what we did. So this is an example. This is actually on a wind farm. They did quite a lot of restoration on the wind farm, and we were interested in using our approach to test it, to just see. We had lots of data from their team in terms of what happened on the ground. And then what you can see, we compared 2 slices of images, the beginning 2015 to 2019, and the second one is 2019 to 2023. The restoration happened towards the end of that period. And what you can see is, see all those areas of black? They've turned blue. Black is degrading, blue is good. So their restoration is bringing back these surface motion amplitudes and the signals that we're expecting to see from good peatland. And you can see there's areas that seem to be kind of lines of stiff. That's the track. And that's where the peat is compacted underneath the track and is consolidated. And at all the areas where they've done restoration, so the 3 arrows in yellow, they've gone from degrading to good. So we can quantify that spatially, and we can tell them X amount of your pixel have turned from degrading to good, so you're on the right track. Or watch out, there's an area that seems to, you've done restoration, but it seems to still be degrading. You might have to go back and do a bit more work there. So we can use that to inform the management of the peatland, but also to make it really cost effective, because we can do, and we have done, the whole of Scotland at once. And we could do slices of years, we could do year-to-year changes, and we can really look at intervention and responsive intervention. So I think that's really cool that we can now incorporate the bog breathing and the understanding of how the mechanics play a role into really large-scale monitoring. It's not the only thing that we need to do, but that's one of the things.
What's happened in the south there, where all the good is turned into stiff?
So this is these are the some of the things that we'll go back and look at. But one of the things that's happened there is that there was an area that was south of the road where they upgraded the track, and it seems like before it was receiving water, and the track cut off the water supply and it dried out. So it went from amplitude quite good to stiffening because of the loss of water supply. But we can go, in real details with the management and look at the different areas and see maybe they need to put a culvert on that road or change or manage the upgrade. And so I think that the key messages that are coming out of that is really that there is new technology out there and we need to embrace it, but I'm a boots on the ground kind of person. And I always want to make sure that if we use these technologies, that we have the real validation and understanding of what they're showing us. Otherwise, there's a danger that we'll get a shiny new product, but we won't know if it's wrong. And that, I think that's been some of the things that I've been really involved in developing. And there's 25 million hectares of peatland degraded, and I think that all the evidence that we have is that what we do in the flow country now, we have a beacon for the rest of the world to see. This is what we've done. We've now got a UNESCO World Heritage Site. We're doing lots of really good restoration and management. We need to ramp that up and put that message out so other people can start doing it and embracing it as well.
Is that a figure for the British Isles or for the whole of right across?
Oh, right
Siberia?
Across Siberia.
Right around, yeah.
But much of the degraded peatland are in Europe. You know, there's not that much in Canada, and there's not that much in kind of Siberia. There is some, but the vast majority are in Europe. And as we do that, I think it's important that we share that knowledge, and that's what I'm doing tonight. But we think again, with the flow country being a World Heritage Site, we have now something that can attract people to come and learn and then go away and take that learning and implement it in other parts. We do that already, but I think we need to keep doing it a bit more. And we also need to make sure that we have skills that can go with what we need. So we're ramping up the restoration, we're ramping up the management. We need people with skills. We need people that can identify the species on the ground, that can know how to operate the diggers, that can do the survey, that can do the GIS, that can use the satellite data. And I think that's really important now that we use this opportunity to build up the skills and bring people in the areas where the peatlands are. So for me, the World Heritage Site is an opportunity to bring people back in the Highlands, people with skills, people that will want to be here and work here and have a career. That's a chance for me to make sure that my daughter has a future. When she wants to go to uni, she can come back because there's a job for her to come back to if she's interested. And we need to share it widely. And this is one of the things that we've been doing quite a lot as well. Is I'm talking tonight, but you're an educated group of people and you're interested in the peatlands, and that's why you're here. But there's a whole lot of people that don't really know anything about peatland, and if you say, do you want to come to a peatland talk, they'll say no. But if you say, do you want to come to an art exhibition, they'll say yes. So if we can bring the peatlands into the arts, if we can bring the peatlands into the wider public, then we can change perception. We can make people realize that no, peatlands are not just fascinating for a very, very small number of people. They're just amazing, and they can be amazing for everyone. And that's how I ended up in Glasgow in front of the Celtic Connection, in front of 700 people talking about peatland. And I think that's really fascinating that we have now an opportunity. The global scene is there now to look at what we're doing in the flow country because it's a UNESCO World Heritage Site. And again, for me, it's I do research, but I do mostly supervise PhD students and postdoc and train them to become researchers. And over the years, we've had, 50 PhD students coming and doing work in the flow country. And these are people that will then go on and take jobs elsewhere and have an influence. And these are some of the people that have provided the data. So, Angela is now a lecturer at the university. She leads the entomology at Forest Research. She was doing the work in the forestry on the moths and the carpet beetles. Renee is the head of Peatland Codes. She was one of my students. Tom, who did all the work on the cores, he's now a lecturer in sustainable forestry. He's the one who found out that the trees were not so good for the carbon. So all of these people that came through the Highlands to do their degrees have either stayed or gone on and have taken really meaningful, impactful position in other places. And for me, that's really important, that we know that we have a place here, that we can really get the future leaders of the peatland and the science world as well. Paul was my first PhD student. He's now a scientist in China, and he's taking up their peatland skills right up now by transferring all the knowledge gained here. And there's more. and if you wanted some talks on birds, he's your man. So he's one of my PhD students at the moment. He was in charge of the seabird census, and he's now working on the recovery of waders and waterfowl in the flow country post restoration. So, and he's really good. He's a really good speaker as well. And so yeah, lots of people. So Pete was one of my postdocs, now senior site manager at Forstenard. So really, I think we have, we have opportunities. We're in the Highlands, and I think sometimes we undersell ourselves as a place where we could really build talent and build skills, and create really good people for the jobs that are needed in the future. Be of luck. Thank you very much.
Is it okay if I ask a few questions?
Of course, yes.
Yeah, that's fantastic. Any questions for Roxane? Val?
Would it have made any difference if the trees had been native species and not introduced conifers? Because haven't there been remains of trees found in bogs that are very, very old?
Yeah, I think there was a period of time about 5,000 years ago where there was a slightly warmer, drier climate where the pine in particular kind of became a bit more, like bits of pines were found a bit everywhere. I think what I say to people generally is it has to be the right trees in the right place. The conifers on the bog were not the right trees and they were not in the right place, but we need more riparian woodland. We need we need woodlands in the areas where there's drainage, where the trees would naturally grow. And I don't think we need forests in the flow country, but there's space for the right trees in the right places. So these were trees that were needed because of the Second World War. There was need to reinvest. There was reinvigorating the economy, and the policy that was designed around it was not perfect. But the power of hindsight makes us think that it was the wrong decision, but we would have maybe made the same decision if we were in the same place at the same time. So I think that going forward, we need to learn from that and know that they are not the right trees in the right place, and we shouldn't be planting on the bog, and we should be mindful of their potential effects in terms of spreading the regen. But we need those trees in the right places. We need to have the shade over the rivers. We need to have the trees in the crags, and we need to make sure that we have not, degenerate forest. We have forests that can regenerate themselves as well with different age and stands.
The regeneration of woodland along some of our watercourses, and we've looked at one, the River Lonan, over the last year, is being severely hampered by the herbivore populations in that area. That's not a factor, is it, over most of the flow country? I mean, there will be places where there's high red deer populations, but does it impinge?
Yeah, it does. In some places it does, but not through grazing, more through trampling. Yeah. So they would travel across the peatland rather than kind of be hemmed in an area for grazing, because there's not much grazing anyway. But they definitely travel through. And what's happening in terms of, say, the restoration is that anyone who wants to go into peatland restoration first has to demonstrate that they have deer numbers under control, because otherwise it would be putting public money for potentially no good, because the deer might destroy the restoration, they might destroy the dams, and they might just bring back the same problems. So there is a big drive for everybody who's involved in the peatland restoration now to really bring those numbers down, and I think more and more people are realizing that it needs to happen. But I think it's less of an issue in some of our areas of the flow country and really big issue in others. So it depends where you are in the landscape. But it's a different pressure. But what it does is that it stops the regeneration of the riparian woodlands. So the trees that would normally grow on those edges of the peatland between the rivers, these, you look at the names in the landscape, and there's the river of the rowan and the burn of the birch, and there's not a rowan or a birch to be seen. So, obviously they should be there. Yeah.
Yeah, but the foundation has an area of peatland that was restored about 20 years ago by ditch blocking, quite a big area. And is it possible to get, and of course monitoring hasn't been ideal because nobody had time, is it possible to get that kind of information from you, what's happening now, whether it's happening or get good beginning?
I suppose yes and no is probably the answer. So, you know, all of the work that we've done with the bug breathing, obviously there's a cost to it. So it's not something that I can just pull out. And so we've done it. You know, the project was commissioned by Nature Scott. We had lots of funding from NARC to develop all of those methods. But, you know, we have done quite a lot of Scotland, and that will come out in a report quite soon. And you could look, is your area included in that? And if it's not included in that, then, you know, maybe this is something that could be complemented. But equally, you know, these are really good student projects. You know, so it may be that if you wanted to do a bit of monitoring, like spot after 20 years, then this could become a student project. And, you know, there are lots of students who are interested in getting involved, and, you know, that could provide some data if that was of interest.
Yeah, going back to trees, isn't there quite a lot of evidence that the natural tree line goes quite a long way up and intersects with the sort of peatland bogland, much higher than, I mean, you suggested it's natural, that it's riparian maybe.
Yeah.
In northern Scotland. What's your view on that? Is the natural tree line higher than people have traditionally thought?
Do you mean higher in elevation?
Elevation, yeah.
Or yeah, I think probably, because you can see it in the cairngorms where they've started to do. There's in Craigmeggy. This is a good example where they've really brought the deer down really low, and they're just letting the trees grow where they want to grow, and they're, you know, probably a bit higher than, you know, than people would have thought. But in terms of where we are in the flow country, there is not that much evidence that there was ever a forest. You know, it was bog. And if you look at the evidence that we have, there was a period of time where there was a bit more trees, but they declined, and it stayed bog for pretty much the whole time. So the Caledonian forest wouldn't have been forest dominated across the flow country. It would still have been bog.
Dean, the mic, sir.
When there is a wind turbine installation and they're considering a planning application for that, does the Highland Council have any conditions where they require of the wind turbine company that they give grants to you to do the restoration afterwards, or companies that you want to?
No, there is not. It's not in the planning application, and we're completely outside of the planning process because we're completely impartial to those decisions in terms of my research. But what is tended to happen is that the planning framework is very clear. They have to produce a plan, a peat management plan. They need to explain what they're going to do, but they don't know what they can do. They don't understand what they can do, so they come to me, and then we have a chat. And I've just 2 weeks ago now, we've got some funding to develop what's called a knowledge transfer partnership. So it's funded by ERI-UHI and a renewable energy company. And what we're going to do is we're going to employ one person that's going to sit with the company, but is going to be employed by the university, and is going to spend 2 years helping them on their journey to learn how they should do their restoration and manage. But this is not before the planning, so I'm never involved up to the point where there's consent. So I'm only involved after. So if a wind farm is consented, then I can work with the developer, and I'm removed from the decision process. It's a very conscious decision because I also don't want to influence the planning process, because I wouldn't want a developer to say, well, we're working with Roxane, so it's going to be okay. So I don't want that to happen. So I always remove myself from that stage of the process.
Amanda, you had a question.
Yeah, traditionally people cut peat for fuel, and the story always goes that actually if it's done on a small scale and it's done carefully and the turfs are replaced on top, that actually the health of the bog is maintained. Obviously there's been a carbon extraction from it, but do you have evidence that that's true? And will the bog breathe again after peat has been cut from it?
So yes, we have evidence for that. So one of my PhD students was doing work, and what we found is it's just a little bit more complicated. It always is. So it depends how much peat is left. So if the peat is being cut below 1 meter, so if there's less than 1 meter, if it's cut right to the bottom, then it's unlikely to recover properly. If there's enough peat that it can kind of stitch back, and then it works really well. Actually, it grows really well in the cut area, but it also depends how good the turfs are put back. And what we've seen in one of the sites in the North Coast is they've now gone with diggers to reprofile the edges. So these are areas where there's no longer peat cutting happening, and they've removed those really sharp edges. And it's really hard to tell that there was ever peat cutting in that landscape, because you wouldn't know if you just looked at it. So I think yes, if it's done carefully, it probably is going to be recovering, but it won't be sustainable in the sense that there's a big loss of carbon. But it doesn't mean that we can't do it, because there's no alternative in some places. So, yeah.
David, I think you had a question.
Yeah, I was going to, so with this survey you've done across Scotland, what are the results in terms of quality of
It's
percentage-wise, how much is good, how much is bad, and what's the direction of movement?
So what we've looked at is specifically all of the areas where there's been restoration intervention across Scotland, and what we're seeing is that you can't paint a picture really simply. So there's a lot of things to unpack, but one of the things that seems to be happening is that the same technique doesn't always lead to the same outcome, because it depends on the landscape position, it depends on the quality of the contractor, it depends on the time of year where the restoration has been done. But what we're seeing is that we can pick out those things really well with the bog breathing method that we've applied, and we can identify areas that we think are behaving not like they should, and then go back and look at the mapping and the evidence, and then we can pinpoint why we think that is. And we think that this is going to be a really helpful tool to identify rapidly, cost effectively, those areas that there's been restoration but they're still degrading. And then we could say, maybe you should go and look back at this one in the field and understand what's happened. Is there a failure? Is there too much deer pressure or something like that? And then you can intervene. So I think that's the direction of travel for this. I can't give you off the top of my head a percentage of what's good, what's bad, what's wrong, but the report will be published very soon.
Yeah.
There's quite a wealth of sphagnum species associated with these communities. I know locally we can pick up to 20 species just in our little peat bogs, but does the distribution of those tell you anything about what's happened to a bog in the past? I mean, is it a useful tool to know which sphagnum species occur where? I mean, I'm thinking of one we call drowned kittens, which is the one that occurs in the pools, but that's a very obvious one. But do other species tell you if you look at them in detail what's going on? Or
yeah, so there's quite a few species that are useful. So for example, if you have Sphagnum denticulatum, used to be auriculatum, is cowhorn bog moss. It suggests overland flow. So if you see a patch of that, it means that there's water going over the top of it. If you find Tenellum, you know that there's been a disturbance, because it likes disturbance. So you can pick out, there's quite a lot of the ecologies that you can pick out, and there's western species that means you're more oceanic influence and things like that. Yeah, so you do that.
You mentioned pulchrum. We don't actually get pulchrum. We've never found pulchrum over in the west. That's an eastern thing, is that?
It's between Lairg. So if you go from Lairg west, it's full of pulchrum.
Oh right.
Yeah.
Oh yes.
But we find it right up until the middle of the flow country, not to the east. So it's like a central west species. Yeah.
We don't get it here. Doesn't occur in Assynt.
I've not found it here.
No,
but
it's not here.
Not looked hard for it either.
Fine.
Well, just a point about denticulatum. I think, could it not also be found where you're getting mineral enrichment from the Atlantic hyperoceanic?
Yeah. But see, if I'm in East Caithness, Monterey, I'm walking on the edge of a pool and I see a patch of denticulatum, I know that water is flowing out that way. Yeah.
I suppose we better bring it to an end, but I've just got my own question for you. I was trying to compare what Assynt is with what you were talking about with low country, and all our peatbogs are quite isolated, as you said. A lot of them have been dug over. You know, there's certain townships where they, in the past, they said there's no peat left because they've been dug over. How does your message apply to Assynt, for example? And also, there's this idea, but you can still plant trees on peat that's only 3 feet. Is that good for carbon, or is that, you know, all these things are going through my head. I don't know if you have any comments on any of that.
Well, I think that, you know, the message I think is that if there are good areas of peatland, they're valuable, and you know, spreading the love about them is important, because then we might protect them from future, you know, land use changes that might impact them. And the other thing is degraded areas. The sooner we can do some restoration intervention where it's possible, the better, because it's going to bring them into a resilient space before the worst of climate change hits. So kind of getting into those, and there's money, you know, there's money at the moment from the public funding sector for peatland restoration. So this is a time to go and look at where can we do these kind of interventions. But, you know, my feeling about trees is that, you know, there's still quite a bit of mixed evidence at the moment, and it seems like it might not be as good for the climate, but it's not just about carbon. You know, some places you need trees for other things in terms of shading rivers, biodiversity, and so it's balancing all of these things is really important, and getting it integrated in the landscape is really important as well.
Is there scope for the World Heritage Site to change the area, to expand, to come over this way, for example? Or?
This is the only World Heritage Site in the world that has the potential to grow.
Oh, right.
Yeah, most of the World Heritage Site natural landscape are highly under threat, and they have a possibility to shrink because bits will, you know, eaten from the edges. But we have lots of areas on the periphery of the current World Heritage Site where there's active restoration going on, and it may be that, and not tomorrow, I'm talking, you know, in a long time, but it may be that these areas come into good enough condition to be incorporated, but, you know, that wouldn't be done without community consultation and all the process, due process that needs to go. But that was one of the comments from the IUCN. They were saying to us that this is a change because normally they don't have sites that have potential to get bigger, but this one does, so, yeah.
That's good. Well, Roxane, I want to thank you very much for your talk tonight. It's absolutely fantastic. I've got loads more questions for you, but it's stirred debate, and all the questions just show. So thank you very much. It's been really good. Thank you.